Okay, so what we're doing today is we're gonna talk very briefly. The lecture shouldn't take too long today. We're gonna talk about valence electrons, what they are, and how many we want. We want 8 in general for the representative elements. We call that the octet rule. And then we'll talk about how many valence electrons each group has. So group 1, 2, 3, and so on and so forth. We're only talking about here the representative elements. Remember, the main group are representative elements of the first 2 groups and the last 6. We'll talk about that. Then we're going to talk a little bit about this thing called oxidation state, or basically what type of ion that atoms like to create. And they do this to get a stable octet, Okay. And then we'll talk about how to identify the oxidation state just by looking at what group they're in. And that's really it. That's what we're going to talk about today. Okay. And then when we're done, you have this assignment here, this 3 PTP. There's some questions to answer in the beginning here. And then you're going to be filling in this table with the family name, number of valence electrons, oxidation number. Okay. And then you're going to, in this part 3, you're identifying each element that's described here. Okay, that's described here. And I'll kind of go over this again after we're done lecturing today. All right. But that's basically what we're doing today. Okay, so let's start really quickly here. Just a reminder, the main group elements. So give it a second to load here, but the main group or representative elements, as we've discussed in the past, are the first 2 columns or first 2 groups and the last 6 groups here. If you recall, the first group is called the alkali metals. The second is the alkaline earth metals. Then we have all of these transition metals in the middle, and the inner transition metals are at the bottom, if you recall. And then we have group 3A, 4A, or this is 13, 14, 15, 16. We don't really have names for those ones. But then in group 17 or 7A, we call those the halogens. And then in group 18 or 8A, we have the noble gases. Okay. And today we're only going to be really talking about these main group elements, representative elements, when we talk about valence electrons. Okay, now these other elements, they have valence electrons too, but they're a little more complicated and we're not going to discuss them at the moment. Okay, so we're going to ignore the transition metals, inner transition metals. We're just going to focus right now on the first 2 groups, the last 6 groups. And again, we're going to be talking about these things called valence electrons. Well, what are valence electrons? Valence electrons are the outermost electrons. Okay, the outermost electrons. So remember we talked about that atoms, their electrons, as Bohr said, were in energy levels. They're different energy levels. So Bohr said they're in energy levels, and then Heisenberg and Schrodinger said they're kind of described the energy levels a little bit better, okay, than Bohr was able to. Okay, but basically the outermost energy level, we call those electrons, we call them valence electrons. Okay, valence electrons. Now, these are important. Valence electrons are really important because they're the ones that are involved in chemical bonding, and that's really what we're going to be talking about next, because we're going to talk about chemical bonding next. And they determine how an element will react, because the ultimate goal of an element is to have a full valence shell. They want to have a stable valence shell. It would make sense. I mean, it would make sense that an atom wants to be like neutrally charged, right? Like same number of protons, same number of electrons. That would make sense, but that's just not the way it is. Okay, that's just not the way it is. For some reason, elements want to have this stable octet. Okay, at least in the representative elements, the main group elements. Okay, so they follow this this rule that most of them want 8 valence electrons. And we call that the octet rule. The octet rule. There are some exceptions to the octet rule, and I'll talk about them, but most of the representative elements want 8 electrons. It just gives it its most stable configuration for whatever reason. Okay, and this is kind of why we actually group the elements the way we group them, because elements in the same group have the same number of valence electrons, or really want to gain or lose the same number of valence electrons. They all want to have 8 valence electrons. Okay, there are some exceptions to that rule, but for the most part, they want 8. Okay, so if we look here, this is a kind of a representation of the number of valence electrons. So everything in the first group, all the alkali metals, they have 1 valence electron. 1, 1, 1, 1, 1. Everything in the second group has 2 valence electrons. Then we skip and we go to group 13, or sometimes we call it 3A, 13 or 3A. All of those have 3. Then 14 has 4, 15 has 5, 16 has 6, 17 has 7, 18 has 8. There's one exception in the 8 here. Helium only has 2. Helium only has 2. Okay, so that's one exception for the number of valence electrons. Okay, so pretty simple. 1 has 1, 2 has 2, then 13 has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7, 18 has 8. The exception here being helium. Helium only has 2. Okay, now each of these atoms, they want to have a full valence shell. They want to have a full outer shell. Okay, so they can do that one of 2 ways. They can give away their electrons, give them up, and if they give them up, then the shell below it then has a full valence shell. So sometimes atoms can give away electrons and then they have a full valence shell left over. The other way is they can gain electrons to get a full 8. Okay, now depending on which is easier, to give away electrons or take electrons, that's what the atom's going to do. It's going to do whatever's easiest for itself. Okay, so if you think about it, for everything in this first column here, right, everything in this first column, they only have 1 valence electron. If they were to lose this valence electron, then the shell below it, the shell below it, the energy level below it would be complete, and they would have a full outer shell. So would it be easier for that first group to lose an electron, 1 electron, or try and gain 7? Because in order to have a full shell, they have to gain 7. They have to get 8 electrons. Do you think it's easier to lose 1 or gain 7? Think about that for a second. Seems pretty obvious, right? It's much easier to lose 1 than try and gain 7, right? If they give 1 away, then they have a full shell. But if they try and gain 7, they got to find 7 electrons out there. That's going to take a lot more energy, a lot more time than just to lose 1. Okay, so everything in this first valence shell, or sorry, everything in this first one, this first column, this first group, they're going to lose 1 valence electron. They're just going to lose 1 valence electron. When they lose it, then they have a complete outer energy level. Okay, same thing goes for the second group. Second group, they have 2 valence electrons. They can either try and gain 6 or they can lose 2. So it's easier, gaining 6 or losing 2. Obviously, it's easier to lose 2 than try and gain 6. Okay, so everyone in this column is going to lose 2. Lose 2. Okay, when most of these elements, Na and below, Mg and below, if they lose their electrons, they have 8 electrons in their valence shell, and they have a full octet. Okay, the ones above it, though, they are kind of exceptions here. Beryllium, lithium, hydrogen, when they lose their electrons, they then have 2 and they're only 2 in their valence shell, but that one's okay because the first valence shell is okay with 2. It just is what it is. It's okay with 2. Okay, then if we look at group 13, 13 has 3. So is it easier to lose 3 or gain 5? Well, 3 is less than 5, so it's easier to lose 3 than to gain 5. So these are going to lose 3. So again, boron will then have 2 in its outer shell, and then aluminum, gallium, indium, and tellurium will all have 8 in their outer shell. They'll all have 8. Okay. And then we get to group 14. This is kind of where we switch over. Now we have 4 in its valence shell. So is it either lose 4 or gain 4? Well, it can kind of go either way. It can kind of go both ways. Most of the time, it's okay. Most of the time, these will lose 4. Most of the time, they'll lose 4. Okay, lead, tin, germanium, silicon really like to lose 4, and they have a positive charge. Whereas carbon, most of the time, will either gain 4 or, well, sometimes gain 4, but carbon actually rarely gives or takes. It mostly shares. We'll talk about that when we talk about bonding. All right, and then group 15, now we have 5. Is it easier to gain 3 or lose 5? Well, again, it's going to be the larger number that's easier to do. So we have 5, we want to gain 3. So gaining 3 is easier than losing 5. So again, the higher number is actually the harder one to do, right? Losing 5 is harder than gaining 3, so these will gain 3. And then group 16 will have 6. Easier to gain 2 than lose 6. And then 17, easier to gain 1 than lose 7. So you can think of it that way. And then these all have complete octets. Helium has a complete outer energy level. The first energy level only needs 2. So these won't do anything. These won't bond. These won't form any ions. Okay, these will have no ions. Okay, so here's the valence. Again, valence electrons 1, 2, 3, 4, 5, 6, 7, 8. Okay. So when I was talking about whether they will lose or gain electrons, whether they will lose or gain electrons, we call this its oxidation number. So the oxidation state is basically the charge on the ion formed when an element loses or gains electrons. Okay, and the reason that they're gained or lost is to form a complete valence shell. Most of the time they want a complete octet. Okay, so they're going to either lose or gain electrons to form that complete octet. Now, typically metals form plus ions. They're on the left side, and they have either +1, +2, or +3. Some +4s. And then non-metals pretty much always form negative ions because they're always on the right. So metals form positive ions, we call those cations, and non-metals always form negative ions called anions. Okay, we talked about those things in the past. Okay, so we look here, everything in this first column, everything here forms a +1 ion because remember I said they have 1 valence electron. In order to get that full energy level, they can either gain 7 or lose 1. It's much easier to lose 1. If they lose an electron, that means they have an extra positive charge, so they have a +1 charge. The second column, they have 2 valence electrons. It's much easier to lose 2 than gain 5, so they're going to lose 2 electrons and become 2 positive. We skipped the transition metals. Most of the transition metals, they all have positive ions, but they have different numbers. They have different oxidation numbers. Some have 1, 2, 3. Some have multiple oxidation numbers. So we won't really talk about that too much. Then 13, 13A or 3A or 3A or 13. Those are +3 ions because they have 3 valence electrons. They like to lose those 3 instead of trying to gain 5. The next group is 4A or 14. Again, they have 4 valence electrons, so they could either lose or gain. The metals will typically lose, and the metalloids will typically lose. Carbon won't really even form ions most of the time, but it can. And most of the time it'll form a -4 ion because it's a nonmetal. Then the next group, 5A or 15, has 5 valence electrons. It's much easier to gain 3 electrons than lose 5. So that's why you have a -3 charge, because you have 3 extra negative electrons. So that's what the ion it's typically going to form. The next one is group 16. They have 6 valence electrons, much easier to gain 2 than lose 6. So they have a -2 valence, -2 oxidation state, or not -2 oxidation number. And then 17 or 7A has 7 valence electrons, much easier to gain 1 than lose 7. Okay, so that's why they have a -1. And then everything here, the noble gases, they have a full valence shell already. So they're not going to form any ions. They're not going to form any bonds. Okay, and that's pretty much it for today. Yeah, that's pretty much it. So what you want to do now is answer these questions as best you can. Okay, fill in this table. You want to write the family name if it has it. I already put Na, the ones that don't have it. The number of valence electrons, this one's really simple. And then the oxidation number, that what ion do they typically form? Okay. And then you're finding out which one of these elements each one of these is talking about. All right, and that's it. That's it for today. If you guys have any questions or any comments, concerns, please feel free to come back into the classroom, but otherwise you all are free to go, okay? And I'll see you all tomorrow. Later, Chase. Later, Wyatt. Later, Lily. Later, Christian. I am not a morning person.